Hey everybody, Dr. A here, and in this video we're going to be giving an introduction and some background information on our subject of statics. So you probably already know statics is typically a sophomore level engineering course that most, if not all, engineering majors at pretty much any university take. And it typically is a degree requirement for most BS in engineering programs and majors. So while all engineering majors generally take a course in statics, there are a handful of engineering majors who use it quite a bit later on in their courses and in their careers. So those majors typically include civil engineering, mechanical engineering, aeronautical engineering, aerospace engineering, and biomedical engineering, who revisit these topics a lot later on, right? Now, in terms of the prerequisite knowledge of a course in statics, it's pretty much assumed that you've had some course in Physics 1, right? Now, for most engineering majors, that's going to be calculus-based Physics 1, but Physics 1, whether it's calculus-based or trig and algebra-based, is going to be mechanics, okay? And so as we go through this first introductory video, I want us to write down some of these key definitions of key terms, because these are terms that we see a lot throughout a statics course, and we need to make sure we understand what they mean and their definitions early on. So as I've said in a lot of my other videos, you need to write this down, right? Listening and watching is usually not good enough. You want to write all of this down so you really remember it. So let's go ahead and get started. Let's start with our first definition, mechanics. So what is mechanics? Well, this is a branch of physics that deals with particles and bodies at rest and or in motion when acted upon by forces, right? So does that definition make sense to us? Well, I hope so, right? Because if you're watching this video and you're taking a course in statics, you should have already had some knowledge or an entire course in Physics 1 where you covered some of these key topics, right? So the mechanics definition is like a family of information, okay? So let's write this down. We're going to say mechanics includes what we call rigid body mechanics. It includes deformable body mechanics, and it typically includes what we would call fluid mechanics. Okay, so when you hear that word mechanics and you think of its definition, we need to think that it includes these three kind of subsets: rigid body mechanics, deformable body mechanics, and fluid mechanics, okay? Now, rigid body mechanics, let's write this down. Rigid body mechanics, that's what typically we label as statics and dynamics, okay? Deformable body mechanics typically includes what we call mechanics of materials. Okay, sometimes you take a course called Mechanics of Materials, or you might call it Mechanics of Deformable Solids, or back in the old days, they would call that course Strength of Materials, but that falls under this category, deformable body mechanics. And then, of course, we have this kind of other subset of mechanics called fluid mechanics. Typically, this would be things involving like hydraulics, okay? hydraulics, or anything that deals with fluid flow. That could also include aerodynamics as well. All right. So as an engineering major, you might end up taking a lot of these courses with these titles. All right. Now, again, for our purposes, we are interested in statics. Okay. So what do we mean by statics? What's the basic definition of statics? Well, statics is a branch of mechanics that deals with the following. So I'm going to say a branch of rigid body mechanics that deals with particles and rigid bodies at rest or with constant velocity. And if you have constant velocity, we know that acceleration would be 0 whenever we have a state of constant velocity. We learned that concept back in Physics 1, okay? So that's statics. What about dynamics? Dynamics is another branch of rigid body mechanics, right? So again, we're studying statics, in this video and in this playlist, but what about dynamics? Well, dynamics is another branch of rigid body mechanics, of course, that deals with particles and rigid bodies that experience acceleration. Okay, so in the case of dynamics, you have an acceleration vector that's not equal to 0 most of the time, okay? So that's kind of what we're going to say to differentiate statics and dynamics. Statics, you're dealing with systems at rest, so your acceleration is 0. But in dynamics, we deal with particles and rigid bodies that are maybe not at rest, so acceleration is not equal to 0. And of course, we are most interested in statics for the purposes of this video and this entire playlist, okay? So let's go through a few more important definitions here. You've seen me write a few keywords here, okay? In particular, I wrote down these two words, these two terms, particle and rigid body. What do we mean by those, okay? So let's define those next, okay? A particle, what is a particle? Well, this is a this is a zero-dimensional object with a mass. It's going to have some mass, which we'll call m, but a negligible size. Particles are modeled as points. Okay, we'll put a comma there. Modeled as single points. That's what we know as a particle, okay? What about a rigid body? A rigid body is a 1, 2, or 3-dimensional object made of several particles that define its shape. And rigid bodies typically also have a mass associated with it, okay? So when we go through our study of statics, we're going to be looking at analyzing particles and we're going to analyze rigid bodies. Now, we're going to find as we go through this, this playlist and this course in statics that some systems, it would be more appropriate to model as a single particle, or maybe sets of particles, whereas other systems are going to be more appropriate to model as 1, 2, or 3-dimensional solid objects, which would be a rigid body. So it's important for now, just know what these two terms are referring to, okay? Now, another term that's really important to us is concentrated force, okay? What is a concentrated force? This is sometimes called, I'll say AKA, also known as a point force, okay? A point force. What this is a load, which again, a force acting at a specific point on an object. And what this is modeled as it's modeled as a vector, okay, or expressed as a vector, okay? And we're going to talk about vectors later on. Okay, so that's a concentrated force. What about weight? Okay, weight is a type of force. We'll say a type of force developed by acceleration due to gravity, which we call G, acting on a mass M. Okay, weight acts in the negative vertical direction. Okay, negative vertical direction. So when we say weight, weight is a specific kind of force, okay? So weight is a force. Now, one thing to remember, and again, hopefully you remember this from Physics 1, weight is a type of force, but not all forces are weights. So we got to keep that in mind, right? All weights are forces, but not all forces are weights, okay? Let's keep going, all right? In terms of our introduction, we need to remember something else from our physics prerequisite, okay? And that's going to be Newton's laws of motion. Okay, this is really important to us as we get our as we start our journey through statics. Newton's laws of motion. Okay, what was Newton's first law? Let's write this down. Okay, first law, and I'm about to tell you. So if you want to try to remember it yourself, you might want to pause the video. But Newton's first law says that, let's change colors here, an object initially at rest or moving with constant velocity will remain in this state so long as no unbalanced force is applied. Okay, so that's Newton's first law. What about Newton's second law? Let's write this down. Newton's second law. Again, if you want to try to remember it on your own, pause the video right now. But Newton's second law says the following: an object acted upon by an unbalanced force F will experience an acceleration A. Let me draw that a little bit better for you. An acceleration A in the same direction as F. The acceleration and force are proportional by the object's mass. Okay, and so this is where we get our famous equation F equals ma. Now in the case of weight, okay, in the case of weight, we can write this as W equals mg. And again, hopefully you remember all of this from Physics 1, but still you want to write this down and really hammer it into your head if you don't remember it exactly, okay? What about Newton's third law? Let's spell that correctly. Third law. So Newton's third law says that mutual forces of action and reaction at a point are equal in magnitude and opposite in direction and collinear when we're dealing with forces themselves, okay? So equal in magnitude, opposite in direction. We know that. We typically recite that quite often in Physics 1 and in statics, but when we deal with forces in particular, they are collinear, which means they lie along the same lines, okay? So, so these are important definitions and Newton's laws we need to remember as we walk into statics from physics, okay? Let's keep talking about some other important background information, okay? Let's talk about base units of key terms, okay? So let's write this down. Base units of key terms. Okay. In statics, we deal with a few specific terms or measurements quite often, and we also deal with two different unit systems of those key terms quite often as well. So as I write this down, I want you to see if you can think faster than me and say it out loud to yourself what these things are before I write it down. So first, let's make a list of the unit system or systems that we're going to talk about. We've got two unit systems that we deal with quite often, okay? What are they? Say it to yourself. So one of them is U.S. customary units, okay? So that's like what we call English units, what we use in the United States. What's the other? The other is SI units, okay? Sometimes we fondly call that metric units, okay? So hopefully you remember that even from high school. Now, what are some of the key terms and, measured values that we deal with in a Physics 1 and now in the statics course? Well, we deal with length quite often. Now, in U.S. customary units, we're going to deal with feet quite often, okay? You could deal with inches sometimes, but we're going to consider the foot as the base unit for U.S. customary length, okay? What about SI units? Well, the base unit we're going to deal with is the meter, which we abbreviate M. Okay, we also deal with time quite often, okay? In both cases, we're going to take the second as our base unit. What about mass? We're going to deal with mass quite often, okay? U.S. customary is the slug, okay? Now, we're not going to deal with the slug very often in our statics course. It might show up every now and then, but just for your information, the unit of mass for U.S. customary is a slug. It's not really a pound. We'll get to pound in a second. What about the unit of mass in SI units? Well, we typically call the gram the base unit, but for our purposes in statics and physics, we often consider the kilogram as the base unit. Some people get kind of upset about that because we have this kilo here, this prefix. And so some people may say, well, the gram is really the base unit. But again, in statics and in physics 1, we rarely deal with quantities that are as small as a gram. We're usually dealing with kilograms and in some cases megagrams. So we're going to take kilogram as our unit that we're going to refer mostly to. But again, in reality, you would think of maybe the gram as a true base unit. What about acceleration due to gravity, G? Okay, well, in U.S. customary units, that's going to be 32.2 feet per second squared. And then in SI units, that's going to be 9.81 meters per second squared. Okay, and then the last, but certainly not least, is going to be force. Okay, so we deal with forces majority of the time in statics. Okay, so the U.S. customary unit of force is going to be the pound. All right. Now, what is a pound? Well, you can express that as a slug times feet per second squared, okay? And then the base unit of force in SI units is going to be the Newton, which we call capital N, and that's going to be equivalent to a kilogram meter per second squared. So be very careful here. When we deal with newtons, a newton is a kilogram times a meter divided by a second squared. A common mistake I see is people think that either a newton is a gram meter per second squared. That's not right. Or they may think a kilonewton is a kilogram meter per second squared. That's also not right. A regular old newton is a kilogram meter per second squared. So be very careful with that. And again, watch out for your units of force in U.S. customary units. We have the pound here. Whereas the U.S. customary mass is a slug. All right. Now, in dealing with all of these units, we have to remember some key conversion factors. Okay, so let's write these down. All right, let's write down some conversion factors that we need to remember. And a lot of these, there's other conversion factors besides what I'm about to write down that you might have to look up at some point or another, but these are the ones that we need to remember. So let's talk about U.S. customary units and conversions. Okay, so the obvious one is 1 foot is 12 inches. Okay, we also need to remember that 1 yard is 3 feet. We're also going to remember, of course, that 60 seconds is 1 minute. All right, and then, of course, 60 minutes is 1 hour. I'm so sorry if I'm insulting your intelligence right now. Here's one that you might not know. 1,000 pounds is 1 kip. And then 2,000 pounds, of course, is 1 ton, but that's also equal to 2 kips, okay? So the 1,000 pounds equaling 1 kip might be something you're not quite familiar with yet, but you want to keep that in mind. We use units of kips. We bundle pounds and by the thousands quite often in statics, okay? Now, what about our SI units, our SI unit conversions? Well, these you might be more familiar with because we've seen these even way back in high school. So if you have 10 to the 9 of something, that is a giga, and we abbreviate that with a capital G. If you have 10 to the 6 power of something, that is a mega, which we abbreviate with a capital M. If you have 10 to the 3rd power of something, that is a kilo. We're probably very familiar with that already. We've already mentioned that. If you have 10 to the negative 2 of something, that is a centi. We're used to seeing like centimeters. If you have 10 to the negative 3 of something, that is a milli. We use a little m for that. If you have 10 to the minus 6 of something, that is a micro. We use the Greek letter mu for micro. And then if you have 10 to the minus 9 of something in SI units, we call that a nano, which we use a little n for that. Okay. So these are our some nice review, hopefully for all of us. What about significant figures? Okay, significant figures or significant digits. Well, we learned all these sig fig rules back in high school. We got it drilled into our heads in our chemistry and physics courses. So how do we really need to use all of these rules as we go through our statics knowledge? Well, we need to be aware of them, okay? But most of the time in statics, it's good enough and generally acceptable to round our intermediate calculations to 4 sig figs and final values to 3 sig figs. The reason why this is usually okay in statics is because we tend to deal with large quantities of force, okay? We're dealing with typically thousands of pounds, kips, tons, or dozens of kilonewtons. Sometimes we're dealing in meganewtons. So we're dealing with these large quantities of force. And so we typically don't have to be as stringent and precise with sig figs like we would have to be in a chemistry course or a physics 1 course or an environmental engineering course, for example. So I'm going to write this down. I'm going to say, while we can observe sig fig rules in statics, it is generally acceptable to round intermediate, didn't mean to scroll there, intermediate calcs to 4 sig figs and final calcs to 3 sig figs. Okay, so generally speaking, that's good enough to do. Now, what you want to kind of avoid is if you're given something that clearly only has 1 significant digit, it's probably not super appropriate to use that in a calculation and then round a final value to 3 or 4 sig figs when you were only given 1 significant digit. But again, we're dealing with values on such a macro scale in statics, large quantities, that the sig fig rules, while they're still important, they typically don't have to be observed as stringently as they would be when you're dealing with much smaller, more sensitive quantities like you deal with in a physics 1 or a chemistry course, for example. Okay, so this is going to wrap up our background video on some key information, some key initial information we need in a statics course to get us started. Hopefully you found this helpful. If you did, please hit like and subscribe and keep watching on to the next videos as we move forward. Thanks for watching.